The objective of this topic is to provide a general introduction to the terms and fundamentals of the shielded metal arc welding process. Welding is defined as a metal joining process wherein coalescence is produced by heating to a suitable temperature, with or without the application of pressure, and with or without the application of filler metal. Although welding is one of the newer metalworking trades, its development can be traced to 1,000 years BC. Forged and welded articles of iron and bronze were found in the Egyptian pyramids. During the Middle Ages, blacksmithing was developed to a high degree, producing many items which were welded by hammering. In the early 1800s, the foundation for gas welding was established when Sir Humphrey Davy discovered acetylene. A second contribution by Davy, the production of an arc between two carbon electrodes using a battery for electrical power, formed the foundation for electric welding. In the mid-1800s, invention and development of the electric generator made electric welding more feasible and led to a number of discoveries pertaining to electric welding during the latter part of the century. By 1925, shielded metal arc welding involved many of the techniques and equipment in use today. Since that time, it and other welding processes have developed into one of the most important processes used in the metalworking industry. Welding is the most important way to permanently join two pieces of metal to make them act as one. A riveted joint in a structure is weakened by the drill holes. Heavy plates are required. A welded joint in the same member adds no significant weight and can maintain the full strength of the material. In shielded metal arc welding, the intense heat of the arc melts the base metal and the end of the electrode. The melted electrode crosses the arc and is deposited in the weld pool to form the weld bead. The melting electrode coating forms gases to protect the molten pool from oxygen and nitrogen in the air. Part of the coating, called slag, solidifies to form a glass-like protective coating on the weld bead. Shielded metal arc welding is done mostly on low carbon and low alloy steels. It is also used for stainless steel, cast iron, copper and copper alloys, and nickel alloys. The equipment for shielded metal arc welding is a source of electrical power, work clamps and lead, electrode clamp and lead, electrodes, and accessories such as a chipping hammer, wire brush, protective clothing, gloves, and helmet. The power source is used to provide electrical power for maintaining the welding arc. This power is maintained through control of the voltage-amperage relationship, which is adjusted by the welder with a current control knob on the face of the power source. There is one basic type of power source for shielded metal arc welding. It is called a constant current welding machine. Now, this means that the power source maintains almost constant current for fluctuations in the arc length. The constant current power source can be a transformer rectifier, or a motor generator. Alternating current, called AC, and direct current, DC, can be used with the shielded metal arc process. Direct current can be used in either polarity, electrode positive, sometimes called reverse polarity, or electrode negative, sometimes called straight polarity. Direct current electrode positive is normally used when deeper penetration is required, and direct current electrode negative is normally used for shallow penetration. The work lead is a flexible conductor which completes the electrical circuit to the workpiece and is usually fitted with a clamp for convenience. It may be attached directly to the work or to the table on which the work is positioned. The electrode lead is similar to the work lead and is attached to the electrode holder. The electrode holder is insulated to prevent arcing. Its spring-loaded clamp can hold the electrode at any one of several angles. Another type of holder is the collet type, which contains a set of jaws within the holder to grip the electrode. Although it holds the electrode at only one angle, the electrode itself can be bent as desired for better joint accessibility. Electrodes come in many combinations of metal and coating to best suit the work to be done. They are identified by a number which indicates these combinations. This course of instruction covers the fundamentals of basic shielded metal arc welding. It is presented in a series of job practices, starting with striking and maintaining an arc, and continuing in a logical sequence to include joints in all positions used by arc welders. Lecture discussions provide related information on safety and health of welders, visual inspection and practical weld test, electrode selection, power sources for welding, welding distortion control, and the low hydrogen electrode and its use. Each job practice is summarized in detail in audio-visual form. Student workbooks summarizing each of the topics may be taken into the welding booth for reference. Tests are given at intervals to measure progress. The 5 essentials for proper welding procedures are correct electrode size, current, arc length or voltage, travel speed, and electrode angle. Electrodes are available in 1/16 to 5/16 inch diameters and in 9, 14, and 18-inch lengths. The electrode size is a measure of control for bead size. The greater the electrode diameter, the larger the weld bead. The electrode size to be used is normally designated in the welding procedure. However, if it is necessary to make a choice of electrode size, the decision is usually based on the thickness and type of base metal. In general, use the largest electrode size possible for the job. Larger electrodes have a higher deposition rate, which allows higher welding speed and reduced cost. The chosen electrode must be operated in the designated amperage range in order to establish maximum operating characteristics. If an electrode is operated above the designated amperage range, the electrode melts too fast. This increases deposition and the molten pool becomes too large to control. The resulting weld deposit is wide and flat, with excessive penetration and spatter. Undercutting is apparent along the edges of the weld bead. If the electrode is operated below the designated amperage range, there is insufficient heat to melt the base metal, and the molten pool will be too small for proper control. The droplets forming on the end of the electrode may bridge to the weld pool, periodically extinguishing the arc. The weld deposit will be irregular and piled up with poor fusion. Amperage is also controlled to a lesser degree by arc length. This is the distance between the unmelted end of the electrode and the molten weld pool. The welder should be aware that a cup is formed on the end of the electrode, which recesses the core wire into the electrode coating and adds to the arc length. Increasing the arc length increases the arc voltage and reduces the amperage slightly. If the arc is too long, the metal melts off the end of the electrode in large globules. These globules wobble from side to side and drop onto the work in the form of spatter rather than as useful weld metal. A wide, irregular bead results with excessive spatter and undercut. The weld metal is deposited on top of the plate with poor fusion between the base metal and the weld. Slag inclusions will probably occur. Shortening the arc length reduces the voltage and increases the amperage slightly. If the arc length is too short, the arc will have a tendency to short out. and the electrode will freeze to the work. The weld deposit will be uneven and high with poor fusion. Slag and gas inclusions will normally result. Travel speed is controlled by the welder based on the appearance of the bead forming in the crater. When the travel speed is correct, the bead forms in an oval shape with an oval crater and uniform ripples. If the arc is broken and the slag removed, the oval shape of the puddle is evident. The welder should watch the back end of the puddle to determine quality results. If the travel speed is too fast, the molten metal does not stay molten long enough, trapping gases and slag. The ripples will be pointed and narrow, with irregular penetration and undercut on each side of the weld bead. If the travel speed is too slow, the molten metal piles up. The bead will be high and wide, with considerable overlap and deep penetration. Electrode angles are used to control the molten metal by using the directional force of the arc. For instance, incorrect work angles can result in a crooked weld bead and an erratic arc. Also, too large a travel angle can result in a similar effect. Travel angle can also be used to control heat. A drag travel angle concentrates more heat on the puddle, whereas a push travel angle reduces heat on the puddle. As the lessons progress, the details of these essentials will be explained where most appropriate. In the early stages, selection of electrode sizes and current is made for the students in order to permit them to acquire some hands-on welding experience, promoting a better understanding of the 5 essentials. At completion of this course, the student will be employable as an arc welder. Further on-the-job training will permit advancement to higher levels of skill. The student will also qualify for advanced shielded metal arc welding.